Good morning, students. Last time you have seen the Carnot engine and its efficiency. Remember here, the four steps of Carnot cycle are isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. And the P-feed diagram, that means the pressure versus volume diagram of Carnot cycle, it is represented as like this. Here, from point A to B, we perform the isothermal expansion process. From point B to C, we perform adiabatic expansion, and from point C to D, we perform isothermal compression, and from point D to A, we perform adiabatic compression. Then this is also the P-feed diagram of Carnot cycle. Here, our system it absorbs Q2 amount of heat at temperature T2 and it receives the Q1 amount of heat at temperature T1. Then the new concept of thermodynamics or a new term that today you are going to learn, it is the entropy. Here, entropy, it is a thermal property. It depends on temperature and remains constant during adiabatic change. And the small change in entropy, it is given by the ratio dq by T, where dq, it is the small amount of heat Q absorbed at temperature T. This is the mathematical expression of entropy. Remember that entropy, it is a thermal property. It depends on temperature. As temperature increases, entropy increases. And mathematically, entropy, it is the expressed as heat absorbed to the temperature, and it is expressed in the units joule per Kelvin or kilojoule per Kelvin, because we express heat absorbed into joules and temperature in Kelvin. That's why the unit of entropy, it is joules per Kelvin. Then entropy, it is a state function. That means it depends only on the state of the system. Suppose we have, this is a reversible process. Our system, it transfers from state 1 to state 2, and the change in entropy, it is also given by here delta S, and this delta sign, it is the big change or finite change in entropy, and it is again the same ratio of heat to the temperature at which heat is absorbed. And remember that the change in entropy, it is given by S2 minus S1, where S2, it is the entropy of state 2 and S1, it is the entropy of state 1. And remember that the entropy of initial state and final state, these two entropies are same. Therefore, the change in entropy, it is 0. Then entropy is a tendency in nature to proceed in a direction that increases the randomness of a system. A random system is one that lacks a regular arrangement of its parts. This tendency towards randomness is called entropy. Entropy is a measure of chaos or disorder of the system. Entropy, it is denoted by letter S and can be defined in a simple qualitative way as a measure of degree of randomness of the particles such as molecules in the system. Then entropy may be defined as property of system which measure the degree of disorder or randomness in the system. In Greek word, entropy means transformation. It is denoted by letter S. Clausius was convinced the significance of the ratio of heat delivered and the temperature at which it is delivered. Again, entropy is a measure of disorder or randomness in a molecular system. It is called as entropy. Examples: when solid changes to liquid. That means when we heat any solid, its orderliness decreases and disorder increases. That's why the entropy increases. In another example, when liquid changes to solid, that means disorder decreases and order increases. In this case, entropy decreases. And in the third example, when gas changes to liquid, here again the disorder decreases, order increases. That's why entropy decreases. Again, all of you know the change in Gibbs free energy. It is given by the equation delta H minus T delta S. Here, this is the Gibbs free energy. This is the enthalpy function and this is the temperature. That means the product of entropy into temperature, and this term it measures the unavailable energy of the system. Here in this Gibbs free energy, the energy that is available to do work, a reaction will spontaneously occur if delta G decreases. That is exergonic reaction. A reaction will not occur spontaneously where the reaction is endergenic. That means delta G is greater than 0. Here this is the equation of Gibbs free energy, and all of you know this Gibbs free energy, it is the energy which is utilized in doing useful work, and it is equal to the enthalpy of the system minus the energy which is unavailable for doing work. Then the physical significance of entropy. Here, as the expression of entropy or mathematical statement of entropy, entropy ds it is equal to dq divided by T. This equation does not tell us regarding the significance of entropy, so that what kind of information we have from the term entropy, it is explained with the help of physical significance of entropy. And as entropy is a thermal property, it depends on temperature. As temperature increases, entropy increases, and hence the entropy it measures the order and disorder of the system. As disorder increases, entropy increases. And in this example, all of you know spontaneous processes are always accompanied by an increase in disorder or randomness of the system. In all such processes, there occurs an increase of entropy. Hence, entropy may be regarded as measure of disorder or randomness of the molecular arrangement in a system. and it is explained with this example. Suppose we have a solid. Suppose for example NaCl solid, and all of you know in case of NaCl it has a cubic structure, and all the Na plus ions and Cl minus ions, they are arranged systematically, regular and periodic arrangement. As we hit the solid here, the regular and systematic arrangement it disturbs. Ale, and solid it will get convert into liquid. That means here order decreases. Again, if we hit liquid, it convert into gas. Again, disorder increases. That means as temperature increases, disorder increases and entropy increases. This is also the same example. Here, let's hit slow motion of the molecules. As we hit any substance, then its kinetic energy increases. Then the application of entropy we will see later on.